Chapter 4. Getting Started with Neural Networks, Classification and Regression. This chapter covers your first examples of real-world machine learning workflows, handling classification problems over vector data, handling continuous regression problems over vector data. This chapter is designed to get you started using neural networks to solve real problems. You'll consolidate the knowledge you gained from chapters 2 and 3, and you'll apply what you've learned to 3 new tasks covering the 3 most common use cases of neural networks: binary classification, multi-class classification, and scalar regression. Classifying movie reviews as positive or negative, binary classification. Classifying newswires by topic, multi-class classification. Estimating the price of a house, given real estate data, scalar regression. These examples will be your first contact with end-to-end machine learning workflows. You'll get introduced to data preprocessing, basic model architecture principles, and model evaluation. Classification and regression glossary. Classification and regression involve many specialized terms. You've come across some of them in earlier examples, and you'll see more of them in future chapters. They have precise, machine learning-specific definitions, and you should be familiar with them. Sample or input, one data point that goes into your model. Prediction or output, what comes out of your model. Target, the truth, what your model should ideally have predicted according to an external source of data. Prediction error or loss value, a measure of the distance between your model's prediction and the target. Classes, a set of possible labels to choose from in a classification problem. For example, when classifying dog and cat pictures, dog and cat are the 2 classes. Label, a specific instance of a class annotation in a classification problem. For instance, if picture number 1234 is annotated as containing the class dog, then dog is a label of picture number 1234. Ground truth or annotations, all targets for a data set, typically collected by humans. Binary classification, a classification task where each input sample should be categorized into 2 exclusive categories. Multi-class classification, a classification task where each input sample should be categorized into more than 2 categories, for instance, classifying handwritten digits. Multi-label classification, a classification task where each input sample can be assigned multiple labels. For instance, a given image may contain both a cat and a dog and should be annotated both with the cat label and the dog label. The number of labels per image is usually variable. Scalar regression, a task where the target is a continuous scalar value. Predicting house prices is a good example. The different target prices form a continuous space. Vector regression, a task where the target is a set of continuous values, for example, a continuous vector. If you're doing regression against multiple values, such as the coordinates of a bounding box in an image, then you're doing vector regression. Mini-batch or batch, a small set of samples, typically between 8 and 128, that are processed simultaneously by the model. The number of samples is often a power of 2 to facilitate memory allocation on GPU. When training, a mini-batch is used to compute a single gradient descent update applied to the weights of the model. By the end of this chapter, you'll be able to use neural networks to handle simple classification and regression tasks over vector data. You'll then be ready to start building a more principled, theory-driven understanding of machine learning in Chapter 5. Section 4.1. Classifying movie reviews, a binary classification example. 2-class classification, or binary classification, is one of the most common kinds of machine learning problems. In this example, you'll learn to classify movie reviews as positive or negative, based on the text content of the reviews. Section 4.1.1. The IMDb dataset. You'll work with the IMDb dataset, a set of 50,000 highly polarized reviews from the Internet Movie Database. They're split into 25,000 reviews for training and 25,000 reviews for testing, each set consisting of 50% negative and 50% positive reviews. Just like the MNIST dataset, the IMDb dataset comes packaged with Keras. It has already been pre-processed. The reviews, sequences of words, have been turned into sequences of integers, where each integer stands for a specific word in a dictionary. This enables us to focus on model building, training, and evaluation. In Chapter 11, you'll learn how to process raw text input from scratch. The following code will load the dataset. When you run it the first time, about 80 megabytes of data will be downloaded to your machine. The argument num_words equals 10,000 means you'll only keep the top 10,000 most frequently occurring words in the training data. Rare words will be discarded. This allows us to work with vector data of manageable size. If we didn't set this limit, we'd be working with 88,585 unique words in the training data, which is unnecessarily large. Many of these words only occur in a single sample and thus can't be meaningfully used for classification. The variables train_data and test_data are lists of reviews. Each review is a list of word indices, encoding a sequence of words. Train_labels and test_labels are lists of zeros and ones, where 0 stands for negative and 1 stands for positive. Because we're restricting ourselves to the top 10,000 most frequent words, no word index will exceed 10,000. For kicks, here's how you can quickly decode one of these reviews back to English words. Section 4.1.2. Preparing the data. You can't directly feed lists of integers into a neural network. They all have different lengths, but a neural network expects to process contiguous batches of data. You have to turn your lists into tensors. There are two ways to do that. Pad your lists so that they all have the same length. Turn them into an integer tensor of shape samples, max length, and start your model with a layer capable of handling such integer tensors. The embedding layer, which we'll cover in detail later in the book. Multi-hot encode your list to turn them into vectors of zeros and ones. This would mean, for instance, turning the sequence 8, 5, surrounded in square brackets, into a 10,000 dimensional vector that would be all zeros except for indices 8 and 5, which would be ones. Then you could use a dense layer, capable of handling floating point vector data, as the first layer in your model. Let's go with the latter solution to vectorize the data, which you'll do manually for maximum clarity. Here's what the samples look like now. You should also vectorize your labels, which is straightforward. Now, the data is ready to be fed into a neural network. Section 4.1.3. Building your model. The input data is vectors, and the labels are scalars, ones and zeros. This is one of the simplest problem setups you'll ever encounter. A type of model that performs well on such problem is a plain stack of densely connected, dense, layers with ReLU activations. There are two key architecture decisions to be made about such a stack of dense layers. How many layers to use? How many units to choose for each layer? In Chapter 5, you'll learn formal principles to guide you in making these choices. For the time being, you'll have to trust me with the following architecture choices. 2 intermediate layers with 16 units each. A third layer that will output the scalar prediction regarding the sentiment of the current review. Figure 4.1 shows what the model looks like, and the following listing shows the Keras implementation similar to the MNIST example you saw previously. The first argument being passed to each dense layer is the number of units in the layer, the dimensionality of representation space of the layer. You remember from chapters 2 and 3 that each such dense layer with a ReLU activation implements the following chain of tensor operations. Having 16 units means the weight matrix W will have the shape input underscore dimension, comma, 16. The dot product with W will project the input data onto a 16-dimensional representation space, and then you'll add the bias vector B and apply the ReLU operation. You can intuitively understand the dimensionality of your representation space as how much freedom you're allowing the model to have when learning internal representations. Having more units, a higher dimensional representation space, allows your model to learn more complex representations, but it makes the model more computationally expensive and may lead to learning unwanted patterns that will improve performance on the training data but not on the test data. The intermediate layers use ReLU as their activation function, and the final layer uses a sigmoid activation so as to output a probability, a score between 0 and 1 indicating how likely the sample is to have the target 1, how likely the review is to be positive. A ReLU, rectified linear unit, is a function meant to zero out negative values. See Figure 4.2. Whereas a sigmoid squashes arbitrary values into the 0, 1 interval. See Figure 4.3, outputting something that can be interpreted as a probability. Finally, you need to choose a loss function and an optimizer. Because you're facing a binary classification problem and the output of your model is a probability, you end your model with a single unit layer with a sigmoid activation. It's best to use the binary underscore cross entropy loss. It isn't the only viable choice. For instance, you could use mean underscore squared underscore error. But cross entropy is usually the best choice when you're dealing with models that output probabilities. Cross entropy is a quantity from the field of information theory that measures the distance between probability distributions, or in this case, between the ground truth distribution and your predictions. What are activation functions and why are they necessary? Without an activation function, like ReLU, also called a nonlinearity, the dense layer would consist of two linear operations, a dot product and an addition. The layer could only learn linear transformations, affine transformations, of the input data. The hypothesis space of the layer would be the set of all possible linear transformations of the input data into a 16-dimensional space. Such a hypothesis space is too restricted and wouldn't benefit from multiple layers of representations, because a deep stack of linear layers would still implement a linear operation. Adding more layers wouldn't extend the hypothesis space, as you saw in Chapter 2. In order to get access to a much richer hypothesis space that will benefit from deep representations, you need a nonlinearity, or activation function. ReLU is the most popular activation function in deep learning, but there are many other candidates which all come with similar strange names, PRELU, ELU, and so on. As for the choice of the optimizer, we'll go with RMS prop, which is usually a good default choice for virtually any problem. Here's the step where we configure the model with the RMS prop optimizer and the binary underscore cross entropy loss function. Note that we'll also monitor accuracy during training. Section 4.1.4. Validating your approach. As you learned in Chapter 3, a deep learning model should never be evaluated on its training data. It's standard practice to use a validation set to monitor the accuracy of the model during training. Here, we'll create a validation set by setting apart 10,000 samples from the original training data. We'll now train the model for 20 epochs, 20 iterations over all samples in the training data, in mini batches of 512 samples. At the same time, we'll monitor loss and accuracy on the 10,000 samples that we set apart. We do so by passing the validation data as the validation underscore data argument. On CPU, this will take less than 2 seconds per epoch. Training is over in 20 seconds. At the end of every epoch, there is a slight pause as the model computes its loss and accuracy on the 10,000 samples of the validation data. Note that the call to model.fit returns a history object, as you saw in Chapter 3. This object has a member, History, which is a dictionary containing data about everything that happened during the training. Let's look at it. The dictionary contains 4 entries, one per metric that was being monitored during the training and during validation. In the following 2 listings, let's use matplotlib to plot the training and validation loss side by side. See Figure 4.4, as well as the training and validation accuracy. See Figure 4.5. Note that your own results may vary slightly due to a different random initialization of your model. As you can see, the training loss decreases with every epoch, and the training accuracy increases with every epoch. That's what you would expect when running gradient descent optimization. The quantity you're trying to minimize should be less with every iteration. But that isn't the case for the validation loss and accuracy. They seem to peak at the 4th epoch. This is an example of what we warned against earlier. A model that performs better on the training data isn't necessarily a model that will do better on data it has never seen before. In precise terms, what you're seeing is overfitting. After the 4th epoch, you're over-optimizing on the training data and you end up learning representations that are specific to the training data and don't generalize to data outside of the training set. In this case, to prevent overfitting, you could stop training after 4 epochs. In general, you can use a range of techniques to mitigate overfitting, which we'll cover in Chapter 5. Let's train a new model from scratch for 4 epochs and then evaluate it on the test data. The final results are as follows. This fairly naive approach achieves an accuracy of 88%. With state-of-the-art approaches, you should be able to get close to 95%. Section 4.1.5. Using a trained model to generate predictions on new data. After having trained a model, you'll want to use it in a practical setting. You can generate the likelihood of reviews being positive by using the predict method, as you learned in Chapter 3. As you can see, the model is confident for some samples, 0.99 or more, or 0.01 or less, but less confident for others, 0.6, 0.4. Section 4.1.6. Further experiments. The following experiments will help convince you that the architecture choices you've made are all fairly reasonable, although there's still room for improvement. You use 2 representation layers before the final classification layer. Try using 1 or 3 representation layers and see how doing so affects validation and test accuracy. Try using layers with more units or fewer units, 32 units, 64 units, and so on. Try using the MSE loss function instead of binary underscore cross entropy. Try using the TANH activation, an activation that was popular in the early days of neural networks instead of ReLU. Section 4.1.7. Wrapping up. Here's what you should take away from this example. You usually need to do quite a bit of pre-processing on your raw data in order to be able to feed it, as tensors, into a neural network. Sequences of words can be encoded as binary vectors, but there are other encoding options too. Stacks of dense layers with ReLU activations can solve a wide range of problems, including sentiment classification, and you'll likely use them frequently. In a binary classification problem, 2 output classes, your model should end with a dense layer with 1 unit and a sigmoid activation. The output of your model should be a scalar between 0 and 1, encoding a probability. With such a scalar sigmoid output on a binary classification problem, the loss function you should use is binary underscore cross entropy. The RMS prop optimizer is generally a good enough choice, whatever your problem. That's one less thing for you to worry about. As they get better on their training data, neural networks eventually start overfitting and end up obtaining increasingly worse results on data they've never seen before. Be sure to always monitor performance on data that is outside of the training set. Section 4.2. Classifying newswires. A multi-class classification example. In the previous section, you saw how to classify vector inputs into two mutually exclusive classes using a densely connected neural network. But what happens when you have more than two classes? In this section, we'll build a model to classify Reuters newswires into 46 mutually exclusive topics. Because we have many classes, this problem is an instance of multi-class classification, and because each data point should be classified into only one category, the problem is more specifically an instance of single-label multi-class classification. If each data point could belong to multiple categories, in this case topics, we'd be facing a multi-label multi-class classification problem. Section 4.2.1. The Reuters dataset. You'll work with the Reuters dataset, a set of short newswires and their topics published by Reuters in 1986. It's a simple, widely used toy dataset for text classification. There are 46 different topics. Some topics are more represented than others, but each topic has at least 10 examples in the training set. Like IMDb and MNIST, the Reuters dataset comes packaged as part of Keras. Let's take a look. As with the IMDb dataset, the argument num_words equals 10,000 restricts the data to the 10,000 most frequently occurring words found in the data. You have 8,982 training examples and 2,246 test examples. As with the IMDb reviews, each example is a list of integers, word indices. Here's how you can decode it back to words in case you're curious. The label associated with an example is an integer between 0 and 45, a topic index. Section 4.2.2. Preparing the data. You can vectorize the data with the exact same code as in the previous example. To vectorize the labels, there are two possibilities. You can cast the label list as an integer tensor, or you can use one-hot encoding. One-hot encoding is a widely used format for categorical data, also called categorical encoding. In this case, one-hot encoding of the labels consists of embedding each label as an all-zero vector with a 1 in the place of the label index. The following listing shows an example. Note that there is a built-in way to do this in Keras. Section 4.2.3. Building your model. This topic classification problem looks similar to the previous movie review classification problem. In both cases, we're trying to classify short snippets of text. But there's a new constraint here. The number of output classes has gone from 2 to 46. The dimensionality of the output space is much larger. In a stack of dense layers like those we've been using, each layer can only access information present in the output of the previous layer. If one layer drops some information relevant to the classification problem, this information can never be recovered by later layers. Each layer can potentially become an information bottleneck. In the previous example, we used 16-dimensional intermediate layers, but a 16-dimensional space may be too limited to learn to separate 46 different classes. Such small layers may act as information bottlenecks, permanently dropping relevant information. For this reason, we'll use larger layers. Let's go with 64 units. There are two other things you should note about this architecture. First, we end the model with a dense layer of size 46. This means for each input sample, the network will output a 46-dimensional vector. Each entry in this vector, each dimension, will encode a different output class. Second, the last layer uses a softmax activation. You saw this pattern in the MNIST example. It means the model will output a probability distribution over the 46 different output classes. For every input sample, the model will produce a 46-dimensional output vector, where output of index I is the probability that the sample belongs to class I. The 46 scores will sum to 1. The best loss function to use in this case is categorical_cross entropy. It measures the distance between two probability distributions. Here, between the probability distribution output by the model and the true distribution of the labels. By minimizing the distance between these two distributions, you train the model to output something as close as possible to the true labels. Section 4.2.4. Validating your approach. Let's set apart 1,000 samples in the training data to use as a validation set. Now, let's train the model for 20 epochs. And finally, let's display its loss and accuracy curves. See figures 4.6 and 4.7. The model begins to overfit after 9 epochs. Let's train a new model from scratch for 9 epochs and then evaluate it on the test set. Here are the final results. This approach reaches an accuracy of roughly 80%. With a balanced binary classification problem, the accuracy reached by a purely random classifier would be 50%. But in this case, we have 46 classes, and they may not be equally represented. What would be the accuracy of a random baseline? We could try quickly implementing one to check this empirically. As you can see, a random classifier would score around 19% classification accuracy, so the results of our model seem pretty good in that light. Section 4.2.5. Generating predictions on new data. Calling the model's predict method on new samples returns a class probability distribution over all 46 topics for each sample. Let's generate topic predictions for all of the test data. Each entry in predictions is a vector of length 46. The coefficients in this vector sum to 1 as they form a probability distribution. The largest entry is the predicted class, the class with the highest probability. Section 4.2.6. A different way to handle the labels and the loss. We mentioned earlier that another way to encode the labels would be to cast them as an integer tensor, like this. The only thing this approach would change is the choice of the loss function. The loss function used in listing 4.21, categorical underscore cross entropy, expects the labels to follow a categorical encoding. With integer labels, you should use sparse underscore categorical underscore cross entropy. This new loss function is still mathematically the same as categorical underscore cross entropy, it just has a different interface. Section 4.2.7. The importance of having sufficiently large intermediate layers. We mentioned earlier that because the final outputs are 46-dimensional, you should avoid intermediate layers with many fewer than 46 units. Now, let's see what happens when we introduce an information bottleneck by having intermediate layers that are significantly less than 46-dimensional. For example, 4-dimensional. The model now peaks at roughly 71% validation accuracy, an 8% absolute drop. This drop is mostly due to the fact that we're trying to compress a lot of information, enough information to recover the separation hyperplanes of 46 classes, into an intermediate space that's too low-dimensional. The model is able to cram most of the necessary information into these 4-dimensional representations, but not all of it. Section 4.2.8. Further experiments. Like in the previous example, I encourage you to try the following experiments to train your intuition about the kind of configuration decisions you have to make with such models. Try using larger or smaller layers, 32 units, 128 units, and so on. You use 2 intermediate layers before the final softmax classification layer. Now try using a single intermediate layer or 3 intermediate layers. Section 4.2.9. Wrapping up. Here's what you should take away from this example. If you're trying to classify data points among n classes, your model should end with a dense layer of size n. In a single label, multi-class classification problem, your model should end with a softmax activation so that it will output a probability distribution over the n output classes. Categorical cross-entropy is almost always the loss function you should use for such problems. It minimizes the distance between the probability distributions output by the model and the true distribution of the targets. There are two ways to handle labels in multi-class classification. Encoding the labels via categorical encoding, also known as one-hot encoding, and using categorical underscore cross-entropy as a loss function. Encoding labels as integers and using the sparse underscore categorical underscore cross-entropy loss function. If you need to classify data into a large number of categories, you should avoid creating information bottlenecks in your model due to intermediate layers that are too small. Section 4.3. Predicting house prices. A regression example. The two previous examples were considered classification problems, where the goal was to predict a single discrete label of an input data point. Another common type of machine learning problem is regression, which consists of predicting a continuous value instead of a discrete label. For instance, predicting the temperature tomorrow, given meteorological data, or predicting the time that a software project will take to complete, given its specifications. Note: don't confuse regression and the logistic regression algorithm. Confusingly, logistic regression isn't a regression algorithm, it's a classification algorithm. Section 4.3.1. The Boston Housing Price Dataset. In this section, we'll attempt to predict the median price of homes in a given Boston suburb in the mid-1970s, given data points about the suburb at the time, such as the crime rate, the local property tax rate, and so on. The dataset we'll use has an interesting difference from the previous two examples. It has relatively few data points, only 506, split between 404 training samples and 102 test samples. And each feature in the input data, for example the crime rate, has a different scale. For instance, some values are proportions, which take values between 0 and 1. Others take values between 1 and 12. Others between 0 and 100, and so on. Let's look at the data. As you can see, we have 404 training samples and 102 test samples, each with 13 numerical features, such as per capita crime rate, average number of rooms per dwelling, accessibility to highways, and so on. The targets are the median values of owner-occupied homes in thousands of dollars. The prices are typically between $10,000 and $50,000. If that sounds cheap, remember that this was the mid-1970s, and these prices aren't adjusted for inflation. Section 4.3.2. Preparing the data. It would be problematic to feed into a neural network values that all take wildly different ranges. The model might be able to automatically adapt to such heterogeneous data, but it would definitely make learning more difficult. A widespread best practice for dealing with such data is to do feature-wise normalization. For each feature in the input data, a column in the input data matrix, we subtract the mean of the feature and divide by the standard deviation, so that the feature is centered around 0 and has a unit standard deviation. This is easily done in NumPy. Note that the quantities used for normalizing the test data are computed using the training data. You should never use any quantity computed on the test data in your workflow, even for something as simple as data normalization. Section 4.3.3. Building your model. Because so few samples are available, we'll use a very small model with 2 intermediate layers, each with 64 units. In general, the less training data you have, the worse overfitting will be, and using a small model is one way to mitigate overfitting. The model ends with a single unit and no activation. It will be a linear layer. This is a typical setup for scalar regression, a regression where you're trying to predict a single continuous value. Applying an activation function would constrain the range the output can take. For example, if you applied a sigmoid activation function to the last layer, the model could only learn to predict values between 0 and 1. Here, because the last layer is purely linear, the model is free to learn to predict values in any range. Note That we compile the model with the MSE loss function, mean squared error, the square of the difference between the predictions and the targets. This is a widely used loss function for regression problems. We're also monitoring a new metric during training, mean absolute error, or MAE. It's the absolute value of the difference between the predictions and the targets. For instance, an MAE of 0.5 on this problem would mean your predictions are off by $500 on average. Section 4.3.4. Validating your approach using k-fold validation. To evaluate our model while we keep adjusting its parameters, such as the number of epochs used for training, we could split the data into a training set and a validation set, as we did in the previous examples. But because we have so few data points, the validation set would end up being very small. For instance, about 100 examples. As a consequence, the validation scores might change a lot depending on which data points we choose for validation and which we choose for training. The validation scores might have a high variance with regard to the validation split. This would prevent us from reliably evaluating our model. The best practice in such situations is to use k-fold cross-validation. See Figure 4.8. It consists of splitting the available data into k partitions, typically k equals 4 or 5, instantiating k identical models and training each one on k-1 partitions while evaluating the remaining partition. The validation score for the model used is then the average of the k validation scores obtained. In terms of code, this is straightforward. Running this with num_epochs equals 100 yields the following results. The different runs do indeed show rather different validation scores, from 2.1 to 3.1. The average, 2.6, is a much more reliable metric than any single score. That's the entire point of k-fold cross-validation. In this case, we're off by $2,600 on average, which is significant considering that the prices range from $10,000 to $50,000. Let's try training the model a bit longer, 500 epochs. To keep a record of how well the model does at each epoch, we'll modify the training loop to save the per epoch validation score log for each fold. We can then compute the average of the per epoch MAE scores for all folds. Let's plot this. See Figure 4.9. It may be a little difficult to read the plot due to a scaling issue. The validation MAE for the first few epochs is dramatically higher than the values that follow. Let's omit the first 10 data points, which are on a different scale than the rest of the curve. As you can see in Figure 4.10, validation MAE stops improving significantly after 120 to 140 epochs. This number includes the 10 epochs we omitted. Past that point, we start overfitting. Once you're finished tuning other parameters of the model, in addition to the number of epochs, you could also adjust the size of the intermediate layers. You can train a final production model on all of the training data with the best parameters, and then look at its performance on the test data. Here's the final result. We're still off by a bit under $2,500. It's an improvement. Just like with the other two previous tasks, you can try varying the number of layers in the model or the number of units per layer to see if you can squeeze out a lower test error. Section 4.3.5. Generating predictions on new data. When calling predict on our binary classification model, we retrieved a scalar score between 0 and 1 for each input sample. With our multi-class classification model, we retrieved a probability distribution over all classes for each sample. Now, with this scalar regression model, predict returns the model's guess for the sample's price in thousands of dollars. The first house in the test set is predicted to have a price of about $10,000. Section 4.3.6. Wrapping up. Here's what you should take away from this scalar regression example. Regression is done using different loss functions than we use for classification. Mean squared error, or MSE, is a loss function commonly used for regression. Similarly, evaluation metrics to be used for regression differ from those used for classification. Naturally, the concept of accuracy doesn't apply for regression. A common regression metric is mean absolute error, or MAE. When features in the input data have values in different ranges, each feature should be scaled independently as a pre-processing step. When there is little data available, using k-fold validation is a great way to reliably evaluate a model. When little training data is available, it's preferable to use a small model with few intermediate layers, typically only 1 or 2, in order to avoid severe overfitting. Summary. The 3 most common kinds of machine learning tasks on vector data are binary classification, multi-class classification, and scalar regression. The wrapping up sections earlier in the chapter summarize the important points you've learned regarding each task. Regression uses different loss functions and different evaluation metrics than classification. You'll usually need to pre-process raw data before feeding it into a neural network. When your data has features with different ranges, scale each feature independently as part of pre-processing. As training progresses, neural networks eventually begin to overfit and obtain worse results on never-before-seen data. If you don't have much training data, use a small model with only 1 or 2 intermediate layers to avoid severe overfitting. If your data is divided into many categories, you may cause information bottlenecks if you make the intermediate layers too small. When you're working with little data, k-fold validation can help reliably evaluate your model.